Welcome back, everyone. We're going to continue today with your pH calculations with acids and bases. Okay, so on our last lesson, we talked about what were acids, what were bases. We used their physical properties, and we also learned about the pH scale and what is an indicator, and how to use them together to calculate visually the pH of a substance. But we also talked about that those calculations are not always correct and are not the most accountable. So today I'm going to teach you, or start teaching you, how to quantifiably calculate the pH of a solution. So for that, we have to talk about this over here. This will be a subtitle for your notebook then. So calculating pH and pOH. We need to go back and talk about the pH scale again. Let me get out of the way. There we go. So, last time we talked about the colors of the pH scale. We talked about acids and alkalines or bases. But we didn't mention anything about these numbers over here. So let me explain that. An acid in the pH scale has a value that goes from 6 to 0. An alkaline or base solution has a pH that goes from 8 to 14. And any neutral solution has 7. Together, they add up to 14. That means that the pH scale goes from 0 to 14. Okay? By excellence, the best neutral solution is water. So, water doesn't really have a perfect 7 value, but for the purposes of this lesson, we're going to think that it does. Okay, that'll make calculations so much easier. So, acids go from 6 to 0, 0 being the strongest acid, and bases go from 8 to 14, 14 being the strongest base. Alright, so okay. Now then, how did we decide how to use these values? How did we assign these values? How did chemists do that? Well, it wasn't like a guessing game, okay? Chemists didn't just decide to use these numbers because they felt that way. After many calculations and using the decomposition of water, they came to these values over here. Okay, so the decomposition of water, or the breaking down of water, yields both hydrogen and hydroxide ions. This is the chemical equation for the decomposition of water. All right, we talked about it before. If I flip it around, then we get this. Okay, it's the same thing actually. So water produces the same amount of hydrogen and hydroxide ions. By many calculations, which I'm not going to get into, chemists deduced that water has a concentration of 1.0 times 10 to the negative 14. If this is true, and this is for water, then the only way that it can get this value is if the hydroxide composition, or the hydroxide concentration of ions, is 1 times 10 to the negative 7. And the same goes for the hydrogen ions. Hydrogen ions are produced in 1 times 10 to the negative 7. Well, negative 7 plus negative 7 equals negative 14. And this is how we derived these values over here, which go from 0 to 14. Okay? So, moving on then, and this is really important, boys and girls. I need you guys to pay attention to this because this is the basis for the rest of the lesson. From now on, we're going to calculate pH by using formulas, and there are many formulas to actually use for these calculations. This is the first one, and is the most basic one. So then, what are the other formulas? If we want to calculate the concentration of hydrogen ions and the concentration of hydroxide ions, we start again with this equation. From here, we can say then that one formula is the concentration of hydrogen, which is this one over here, times the concentration of hydroxide ions is equal to 1 times 10 to the negative 14. Okay? Sorry. And from this formula, we can get two more formulas. Hydrogen concentration equals 1 times 10 to the negative 14 divided by the concentration of hydroxide ions. It's a simple displacement of the formula. Okay, we're simply clearing the formula to find hydrogen ions. Same goes for hydroxide ions. If we clear the formula to find the concentration of hydroxide ions, then we get 1 times 10 to the negative 14 divided by the concentration of hydrogen ions. Okay, so these are our next three formulas. Sorry. Next, for calculating pH and pOH, keep in mind that pH is the hydrogen potential, or hydronium potential also, while pOH is a hydroxide potential. Okay, so let me go back a little bit over here to the pH scale. Sorry. No substance, no solution is completely acidic or completely basic. It's almost impossible, at least naturally. So that means that if a solution has a pH of, let's say, 6, okay, what happens to the rest of the values then? That's because just as a solution has acidic characteristics, it also has basic characteristics. Okay, depending on which one is greater, it will determine if the solution is an acid or a base. So keep that in mind. Every solution has acidic characteristics as well as alkaline characteristics. The one that is greater will determine if the solution is an acid or a base. Going back to this then, we start off again from this formula over here. Keep in mind that this is the hydrogen concentration and this is the hydroxide concentration. If pH is determined by the concentration of hydrogen ions, then we can simply say this: pH plus pOH, which is determined or depends on the concentration of hydroxide ions, equals 14. Why 14? Because we got this value over here. Okay, so let me just repeat that. The constant pH depends on the concentration or the production of hydrogen ions. pOH depends on the concentration or the production of hydroxide ions. The more hydrogens that a solution produces, the more its pH. The more hydroxide it produces, the more its pOH. pOH is like the opposite of pH. It's like acids and bases. They're both opposites. So, from this formula, we can get two more. By clearing the formula again, we get pH is equal to 14 minus pOH. And pOH is equal to 14 minus pH. Again, we're simply clearing this formula to find the variables of pH and pOH. Okay, so finally then, if we can use the other formulas to calculate pH. But what happens then if we only have the concentration of hydrogen or hydroxide to work with? Well, for this we got two formulas. If we're working with an acid, to calculate the pH, we need to put this formula into our calculators. The negative logarithm of the hydrogen concentration. Okay, don't worry about too many numbers right now. We'll get into that in the next video. Now, to find the pOH, if we're working with a base, then you need to calculate with your calculators the negative logarithm of the hydroxide concentration. Okay, the negative must always be outside of the parentheses because these two answers are always going to be negative, always. But we cannot have a negative pH or a negative pOH, which is why the negative is outside. But what happens if we want to do the opposite? What happens if we want to calculate the concentration of hydrogen or hydroxide from pH or pOH? That means that in here we are starting with the concentrations, but in this case we are starting with the pH or the pOH. If you're working with an acid, the concentration of hydrogen ions can be calculated by doing the negative logarithm, or 10, to the negative pH. Again, don't worry too much about numbers right now. I'll explain that in the next video. And if you're working with bases, then you want to calculate the, this should be a negative over here. I'm sorry, my mistake. If you want to calculate the concentration of hydroxide ions, then you do the negative or the anti-logarithm, which is 10, elevated to the negative pOH. Okay? Those are the formulas that you need to calculate whatever you need. In the next video, in your next part of this lesson, I'm going to teach you guys how to use these formulas. These formulas are interconnected between one another. Okay? And you can find whatever you want with them. You can find the concentrations of hydrogen or hydroxide. You can find pH. You can find pOH. It's just a matter of playing with the formulas and knowing what is given to you in the exercise. So, please copy this and try to organize it as best as you guys can, because this is going to help you a lot for this lesson.